There we go. Alrighty. So first of all, thanks for inviting me here, and thank you for lots of people who helped out with this, and also a big appreciation for people who actually allowed me to talk about this, because this is kind of a little touchy. I'm not going to talk about anything like objectives, because apparently one of the rules is you don't talk about the objectives of your team, of your company, in public talks. So why do we need rules of machine learning? So Google is a big company, and there's lots of products that use machine learning. And if there was a mistake to be made in machine learning, we probably made it at least once. And so we hope to learn from that and not make the same mistakes over and over and over again. So the guiding principle behind these rules that I'm going to talk about in a little bit is the key to building a great machine learning system is to be a great engineer. So how do you be a great engineer? You keep it simple. You document your code. You test it to make sure that it works correctly. You fix the inevitable sign mistake. You have peer review. You have other software engineers or scientists look at your code. You version control. You monitor performance. And then you have a tight launch, innovate, test cycle. So a bunch of times in this talk you're going to ask, is this about reliability? So there is a concept of stable performance. There's also a concept of technical debt, as well as something we care about a lot at Google is just rapid progress and stable progress. It's really hard to sort of pull these all apart, so I just kind of put them all together. Another caveat with regards to this talk is we put a lot of stuff on web pages at Google, so there's a slight bias towards that in this talk. I apologize. So I'm going to start with talking about what you should think about before you even begin doing machine learning. Then I'm going to talk about the basics of when you're launching your first pipeline, what you should be thinking about. I'm going to talk about an issue called training, serving, skew. That's what we call it at Google. It's just sort of the difference between the data that you train on and what you actually see in production. Then I'm going to talk about what to do when you get stuck, and a few rules that aren't necessarily best practices, because I wouldn't say enough people are doing them to quite call them best practice at Google. So the structure of this is based on a document that we wrote, and I'll show you a link to it at the end of the talk. It's all arranged by rules, because it's nice to have a nice succinct statement that you can share with someone that they can then share with somebody else. And this is useful when you're trying to spread information in a company as large as Google. So the first rule is don't be afraid to launch a product without machine learning. A lot of people are like, oh, we're going to build this great product and it's going to be great because it has machine learning. And that runs into a little bit of a problem, because machine learning isn't a magic hat that you can pull a rabbit out of. You don't just get decisions from nowhere. You have an objective, you have past data, and you combine those to create your decisions. And so, for instance, if you were going to build something like a ranking system, and you wanted to retrieve documents, and you wanted to do it with machine learning, before you use the machine learning, use some simple heuristic. Rank by recency, or stars, or anything, or relevance. Then gather your data together. And now that you have the data, you do the learning. This is kind of crucial to a lot of the stuff I'm going to talk about later, that you actually are training on the data that comes from the problem that you're trying to solve. Make metric design and implementation a priority. So before you even think about actually trying to do any machine learning, try to come up with some metrics. Try to define what you're trying to do. And don't worry about getting one metric or one objective right out. Come up with a whole bunch of metrics. If you go to the doctor, they don't just have one number that describes how healthy you are. They have tons of numbers. And that's the way you should think about it. Because your product isn't just something which produces money. It's a patient. You want to keep it healthy. You want to keep it around for a long period of time. The next rule I want to point out, because we might all think this is intuitive, But when we come to machine learning, people think about it as sort of really complicated. But in reality, you can think about using machine learning to reduce technical debt. So for instance, suppose that your first heuristic, like you're building something like a Google Play search store, was to use the number of installs and rank things by the number of times they were installed. And then later on you went, oh, well, how much people like them is more important. And then you start to say, oh, well, maybe I want to mix these up in some crazy thing and raise something to the 2/3 power. Again, not actual objectives. So at some point, the heuristic becomes way more complicated to understand than the machine learning system. And at that point in time, you really want to be, as your heuristics get more and more complicated, you want to shift over to the machine learning system. So, like one other way to think about this is that you've got you can think about it like compilers, right? We used to all write machine code, and that was hard, and it was difficult to debug. And if you had a new system, then you had to rewrite it from scratch. And now we use C++ code, and we can switch systems, and it's all much easier, and so forth. There's an analogy to machine learning here, where you have an objective that's much easier to understand, much easier to transform. And when you apply it to the past data, much like if the past data changes, then your system will automatically, dynamically change to handle it. So instead of hand coding decisions and policy, that's like writing machine code. You don't want to be doing it. And feature engineering plays into it. So and basically, this is sort of one thing I would want to point out. Is imagine that you have some sort of informal goal. I want to get people to get great apps with Play Search. And I could have two kinds of different ways I could think about that formally. I could say what I want. I want to maximize the probability of an install given a search. It's kind of clear what I'm saying there, it's clear what I want to do. But for the next person who walks in the room when I've left the company or whatever, they know what I want it to do. Or I could describe how to get it. Let's take the number of installs, number of views, let's create a decayed number, just blah, 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 and there's all these heuristics, and it's just much easier. And so, at a large enough scale, what you want the system to accomplish is easier and more efficient to express formally in how you want the system to accomplish it. And so I think if we're going to talk about reliable machine learning, we have to at the very least acknowledge that there are other alternatives, and we have to be able to compare ourselves to them. And I think we can win in this particular way, in this particular field. All right, so there's lots of rules here. I'm going to talk about only a subset of them here. So this is an important one for academics. When you go into industry, you're thinking about building great learning algorithms. And you're thinking you're going to spend all of your time focusing on the algorithm and how it's learning. A more accurate reality of what happens is that you're going to spend a lot of time gathering the data and making sure that the data is solid. And you're going to spend a lot of time making sure that when you apply the model, that it's doing the same things that you would expect when you're gathering the data. This is incredibly important to have a realistic view of. And along the same lines, be careful about drop data when copying pipelines. So here's a real example. Google Plus was really excited about building a machine learning system to rank all of their documents. So all of their posts. And so what they had the reason they were excited about this is that they've been successful with the what's hot part of Google Plus. And so what they did was, well, they need to build this whole new system. They already have an existing system. Let's just copy the what's hot stream, the green one, over pipeline to a pipeline for all the systems. And so then, they thought about what they were trying to do. They were trying to rank all the data. They didn't care anymore as much about freshness, which was what hot was about. And it went well, and they launched it. And then later on, they realized that in What's Hot, they were filtering out older documents that had been posted a long time ago, because What's Hot was about giving people fresh content. They left that part in. And of course, that's completely unreasonable in this new pipeline. And I'm not calling out Google Plus engineers. This happens all over the place. These pipelines are somewhat complex, and so you have to be careful, especially about drop data, because drop data, by definition, is data that you do not see. So there was another example that's pretty common. So a lot of times when we log examples, we are caring about predicting the behavior of our users. So if if the user doesn't see it, we sometimes drop it. So there was one team that was doing this very reasonable policy of dropping the examples not seen by the user. But then they wanted to predict whether or not something was shown to the user. When they tried to use copy over the pipeline, they ran into a problem because they were dropping the examples that weren't seen. And finally, there was an issue with Google Play. Google Play reuses a lot of code between ranking books and movies and apps, and they one time accidentally copied over the data along with the rest of it. And so you have to be careful. All right, if there's one rule that's really important, I'm going to say this is like the most basic. Imagine you have a learning system and it's pumping out models continuously, and it's just throwing them out there to your users. And all of a sudden, one of the models is broken. And you send it to the users. This is a nightmare scenario. You will get paged in the middle of the night, or someone will get paged in the middle of the night. Whereas if there was a problem in the learning and you hadn't exported the model, maybe the model might get a little bit stale because you haven't updated it a little bit, but it's not an emergency. You can deal with the problem that you're facing. You don't have to fight the fire. So how do you deal with this? How do you make your life a little more relaxing, where you can wake up to an email that the system is broken rather than at 9 a.m. as opposed to a page in the middle of the night? You can put in a gatekeeper. You can put in a validation system, which checks each model as it is being produced and just does some basic sanity checks. Does this model actually work? Can you actually run it? When you look at the performance of the model and you compare it to the model you're currently using in production, is it any better according to some basic checks that you can do? All right. And if it doesn't, you drop it. And then you might not even fire an immediate alert because maybe the next model is good. Only if you have several models that are failing and when your system gets really stale, do you even have to let anybody know what's happening. All right. Now, another thing which is really important when you're talking to software engineers is software engineers are used to working with systems like email. So for instance, imagine Alice is sending an email to Bob using your system. And the email disappears into the ether. So what happens? If it's an important email, Alice will ask Bob via one of the million other ways we can talk to each other, did you get my email? Bob will say, what email? So there'll be an obvious thing. If this particular email didn't get sent, you can go and you can find out what happened. On the other hand, in our machine learning systems, it's much more nuanced. So when we're generating data, training data for the learner is going to come up with some model. And if that model isn't quite right, exactly which example or exactly which feature was wrong is incredibly difficult to find out. Similarly, when we're gathering features for examples to be classified, and for instance in the production system, that is another tricky part. And so you really need to be monitoring that data and making sure that it's correct. All right, don't overthink which objective you choose to directly optimize first. So I kind of left this one in. There's a bunch of different stuff about objectives, because I think that thinking about objectives is one of the biggest discrepancies between working in industry and working in academia. So we like to think that there's one right objective in academia. But in reality, suppose you care about clicks and time spent. You're not quite sure which one's the right one to optimize, or maybe you want to optimize a mixture of them. And right now you're running a heuristic. 9 times out of 10, suppose that you just optimize clicks. You're going to see that the time spent is also going to increase. Because all of these things are just basically proxies for, is the system better? And so don't really overthink and try to get the perfect objective first. Just get an objective first. And you can leave it around for a while. It's only when you sort of get to this Pareto frontier, when you've added all the basic features, that you really need to start worrying about the balance between clicks and time spent. All right. This, I think, has a lot to do with reliability engineering. Choose a simple, observable, and attributable metric for your first objective. So first of all, simple. Maximize clicks versus some crazy thing. That way, you don't have to worry about, it's very clear what you're trying to actually predict. Observable. So you want to choose something like click or purchase versus, is the user happy about this? Is he satisfied? Yes, you can get to that. Yes, that's an important question, but first get your whole infrastructure set up first. Get your first model out there before you start worrying about such subtleties. And finally, attributable. Click versus time spent on product in the next week or the daily active users. If I'm looking at something like a click or a purchase, I know that the reason you clicked it is because I showed it to you, and if I hadn't showed it to you, you wouldn't have clicked on it. And so it's very easy to figure out what decisions led to what positive outcomes. So, and this is, and again, I emphasize, this is for your first objective. You can go crazy later, but for now, just get it. Okay. All right, so, starting with an interpretable model makes debugging easier. So for instance, choose a model where your average prediction is going to equal your average label. In other words, don't start with a 7-layered neural network, factor model, ranking loss function. Okay? Here's a very important one. Log features at scoring time. So you've got a document ID and a query, and you've got some features for this document. Some of them are going to be things like title. Some of those things are going to be like the impressions that you have, or number of impressions, or number of comments. And you do a join, and then you log the examples or the instances that you were going to score. And then later on, you're going to do a join with the label. And then you're going to put that in your training data. Now, one caveat here that makes this people a little bit frustrated is, after you do the join, sometimes you're going to filter out either the positives or the negatives. Often, like for instance, you'll have way more negatives than positives. So what people do is they come up with this far more complicated scheme, where they log, instead of the whole joined document, they log only the document ID and the query, expecting to do another join offline. This just leads to problems, and it's not worth the savings in resources. And we've seen dramatic improvements in some teams, simplifies the code, and on occasion improves performance because, okay, skip this one. All right, so don't waste time on new features if unaligned objectives have become the issue. So for instance, you add a feature, you train a model, you improve an offline objective, but then your side-by-sides look bad. Or, maybe the side-by-sides look good, but you're losing on other metrics. Something is wrong. People aren't, like, with your system, don't keep trying to add features. Now's the time to tune the objectives, right? So like I said before, don't worry about your objectives early on. Now's the time to worry about your objectives. If just optimizing this objective isn't working on the other things. And this relates to reliability in the sense that it's also showing you that this one objective that you're working with isn't actually representative of everything that you care about. And I think this is probably one of the things that it took me a very long time to understand going to industry, which is launch decisions are a proxy for long-term goals. So we have all these short-term metrics, like clicks and conversions and stuff like that. And we think, and if you come in and it's your first project, you're like, okay, I'm going to increase the accuracy on predicting clicks, and it's going to be awesome, and it's going to launch. But then there's all these A/B tests that they run, and there's all these downloads per day, revenue per day, and they're like, oh, well, that metric went down, and I'm not comfortable with this launch, and so it's not going to happen. Why can't you decide on one metric and we can translate it into a single objective and then we can maximize it? And the reason is that all of these different A/B tests that we're doing are actually a proxy for the health of the system. Because what they really care about is satisfying user, increasing users, satisfying partners, profit, for the long-term goal of having a useful, high-quality product and a thriving company, say 5 years from now. So if you want to apply the reward hypothesis here, it's that the reward is have a product 5 years from now. And that is a tricky reward to work with. And so there's human beings that are in the loop that connect that reward to your A/B tests. And they're thinking about the health of the product because they want it to last. And then you can have engineers who are working on trying to improve those A/B tests through trying to tweak and tune objectives. Okay. So this is, in terms of reliability, this is one thing that I think would just make so much difference if we did it. But it's hard to convince people to do because it's so manually intensive. Well, it's not that manually intensive, but it is manual. So you go like once a week, look at how your system is doing. Just kind of glance around, poke around, see how it's doing. So often I'm just looking at a pipeline, I'm like, wait, there's something wrong here. This looks completely wrong, and you find something. The second one, this is something that surprises me. Consider the learning stability. So if you have a model that you're retraining or that you have like sort of some random initialization, maybe try it with a few different initializations. We often do this in academia, but then we predict the mean. Okay, I think that should be perfectly fine. So we predict the mean And we say, oh, we moved the mean by that much. But then we don't actually think about the overall distribution performances that we could have. And if you're building a vision system, like that you're going to be retraining every 3 months, that doesn't matter. But if you're building a system that you have to update like every week or every day, and you don't quite know whether it's going to be really great or really awful on any given day, that's a problem. And it causes two problems. Because the first problem is that, well, your system might look very bad even to users on that day. And the second problem is, if you want to be innovative and you want to be launching new features, then if you don't even you can't trust how good those models are on any given day, you can never really innovate for any delta that's smaller than the delta that you're going to see between different variations of the same model. So this is incredibly important. All right, and the last unwritten rule that I'm going to talk about today is have business logic and machine learning play nicely together. So for instance, suppose you're going to rank a bunch of documents and you're going to predict the probability of click, and you want to maximize the number of clicks. Well, ranking them in the order of the probability of them being clicked on works perfectly well. If you have the best model that's predicting the models, those probabilities of clicks perfectly, that's the best model that you want to do. If you have constraints where certain, based upon contracts with different companies, certain things can't be in certain positions, that also works fine, as long as you optimize around them. If you multiply it by a utility, like not all clicks are created equal, maybe because of prices or whatnot, then that also is, like, the perfect model makes the best system. On the other hand, you'll often see a prediction times a heuristic, or plus a heuristic. That's fixing something which is not quite right with your model today. But then if you fix that in your model, it might make the overall system worse. And so just be aware of this and try to keep people aware of this. So in conclusion, the key to building a great machine learning system is to be a great engineer. And this is the doc that this is all around. And last point, thank you to my daughter who let me come here and talk to you on her birthday. I really appreciate that. She gets 2 birthdays out of it, so I don't feel too sorry for her, but nonetheless, she's awesome. Anyway, thank you. Questions?
So if there's any questions, I can bring the mic to you.
Hi, I'm curious what kind of standard procedures there are to do sensitivity analysis and learning stability analysis that currently exist inside of the sort of machine learning workflows and the engineering workflows. I know they exist outside of machine learning, and I've used these, but I'm just curious if you know any that maybe add to my tool set.
So I'm sorry. So basically, I mean, as I said, like one of the things we do is validation, right? So if there is a bad model, we don't launch it, right? That's sort of our first cut that keeps us mostly honest. There's also, and I think this is no secret, a ton of A/B testing at Google. And I think a lot of times we'll also use systems, models that we know up front are going to be more stable. We're starting as the deep learning age is evolving. We're realizing that this is going to actually involve a little bit more understanding of stability, and so those types of analyses are under active development.
Hi, great talk. You talked a little bit about the training and serving skew.
Mm-hmm.
Can you elaborate a little bit more about what are the strategies you guys apply to alleviate that?
So here's a list. You can go to the document for more. I mean, there was one thing I would point out that I was going to talk about, but cut for time, was be aware of the inherent skew in ranking problems. So for instance, if you're doing ranking and you're only looking at the data that you show to users, there's an inherent skew in that. And that can create a problem. So we have a variety of different techniques that we do. So for instance, for Gmail autocomplete, where you're typing in a name like Adam, and then when you type the A, we're going to show you like the top 6 names that we think you might be wanting to autocomplete to. You could say that those are the one you click on is the positive and the other 5 are negative, but realistically, the rest of your contact list are the negatives. And so doing switches like that is a way to deal with one particular part of training certain skill. There's a whole bunch of them. This is avoid feedback loop positional features is a very good one. And logging features at serving time actually solves a whole host of problems. And there's a whole bunch of things you have to think about if you don't do that.
I had a question. So, do you ever run into situations where metrics based on human grading or annotation are disagreeing with user engagement metrics, and so do you have a strategy or a set of tools to kind of resolve that discrepancy?
So that was rule 3 or something. So one thing we've noticed before is that you've got things like relevance and the diversity of the actual results returned and personalization. These are all things that people who are working on a product care about. And you would think that they directly translate to actually having clicks improve, and it doesn't work out as easily as you would think. And so often there are techniques for basically trying to have humans in the loop that actually you send off your results to some person you pay to just score whether or not the document was relevant, and then you use that to sort of as a judgment. It's tricky to actually use it during the optimization because you get very little data, but you can use it as a metric when you're looking at the resulting model.
Actually, if I could just jump in as a follow-up question there. So when you have these humans that are scoring things for you, do you give them specific guidance on how to rank things? I can imagine that humans might be worse than some deterministic proxy.
So I think that's so yes, we give them very detailed instructions. And so I hope. And it evolves over time. And it's probably one of the messiest parts of making a launch decision. And I think I would really like to see innovation in this area because, Randy Pausch, when I was in grad school, said, computers are getting faster and faster, but humans are not. And so, this is a very human, very, very time-intensive part of the process, and we need to make it better.
We have still time for a couple more questions. Did you have? Oh.
Thanks for the talk. So, I'm sure you're aware of the significant challenges in particular in putting neural network models into production against simpler models that we've been using for longer. How close do you think we are to having more general frameworks for creating products from neural network architectures, arbitrary neural network architectures, and using, so for instance, independent neural networks per client or customer install instead of sort of some of the systems that use a larger model for multiple clients or customers.
Okay, so I think there were two, there's how do you get neural networks to work? So if you think of clients as being products, then we have TensorFlow, and you can use that for, you can have a different TensorFlow model for each product. And we have Servo, which you can use to serve it. And since we're talking, I like to stay away from particular implementation details here, but yeah, so we do have those two different things. In terms of having individual neural network models for an individual client, I don't know how much I can say about that one, so I'm just going to leave it because it looks like it's about your time to start.
Yep. So let's thank Martin again, and thanks for all the great questions. And so the main workshop